Okay, welcome everyone to our space webinar series, and this will be our penultimate webinar for season 2. And this webinar is being given by Prof. Marvin Doyley. And let me give a brief introduction. Marvin received his PhD degree in biophysics from the Institute of Cancer Research at the University of London in 2000, and in 2008 he joined as a faculty in the Department of Electrical and Computer Engineering at the University of Rochester in New York. He is currently the department chair and a professor in the Department of Electrical and Computer Engineering, with joint appointments in biomedical engineering and imaging sciences. His parametric imaging research lab at the University of Rochester concentrates on non-invasive vascular imaging, model-based intravascular ultrasound elastography, and high-frequency nonlinear ultrasound imaging. He's a fellow of the American Institute for Medical and Biological Engineering, and he also serves on the editorial boards of many journals, including IEEE Transactions on Ultrasonics, Ferroelectrics and Frequency Control, SPIE Journal of Medical Imaging, etc. And for this talk, he'll be speaking about elastography from theory to practice. And that's it for my introduction. We very much look forward to your talk, Marvin.
Okay, well, thank you, everyone. I wish I could see you all in person, together, but I appreciate this honor for giving this talk. So as Sai said, I'm going to talk about elastography. I'm going to kind of take a kind of tour of elastography, and I'm going to focus mainly on the kind of computational aspect of elastography, since I think that would be more relevant for this audience. And I'm going to divide my talk in kind of 3 main areas. So first, I'll just give you a background into why we do elastography. I'll talk a little bit about image reconstructions, solving an inverse problem in elastography, and we'll talk a lot about how different strategies we use to get prior information to stabilize that inverse problem. And then we'll talk a little bit, I'll talk a little bit about a couple of applications, and then I'll conclude. Okay, so before I start, because I always mess this up, whenever I give talks, I always forget the people who really are the ones who really make this happen. And so these are the different, on the top row, these are previous PhD students, and they have at some time or another I'm going to be talking about some of their work. And in the bottom row, so we have Enan, we have Mike, we have Narges. They're kind of collaborators who I've worked with. These are students who are in some of my collaborators' lab. Enan is working with me, and we'll talk about a little bit about their work. And then there's a bunch of professors who I've worked with, from a biologist, Slava, he's in a biology, Steve McAlevey, he's in BME, and we do a lot of ultrasound together. Tom Howard, he's a roboticist, and we've been doing some cool stuff with him, and we'll talk about some of his work. Giovanni Scafito, he is a neurologist, and a lot of our vascular work, Giovanni and I have done a lot of stuff for the last 10 years together. Mujdat, I think most of you know Mujdat. We're working with Mujdat with machine learning on this, in terms of solving inverse problem. Brian Pogue, he's at Dartmouth. Again, a very, very long time colleague. I think I know Brian for about 20 years, and we've been doing a lot of stuff both in the ultrasound area and also optics. And Scott Gerber is an immunologist, and we've been working with him on pancreatic cancer, trying to use, and I'll have one slide describing the work that we're doing with him, where we're using parameters that were derived using this computational framework and trying to see if we could use it to characterize tumor microenvironment. All right, so now that I got my collaborators and my students and former students out of the way, I will start. So elastography, what elastography tries to do is really to characterize mechanical properties of tissues, right? And the idea of characterizing mechanical properties is not really new. It's been around for several centuries, and you can see the image on the left. This was in the Roman time where you had a sick person here, and you'd call a doctor. The doctor would basically feel this person's arm or the limb which they think, or the area which they think is hurted, and try to make a diagnosis. And on the right, you see this gentleman here, basically feeling the pulse, feeling the arms, and trying to make some kind of diagnosis based on touch. So the idea here is it's a classic technique. Doctors still do that. Many of us, when we go to do a physical examination, what you'll find is that the doctors will palpate. And what they're really trying to do is trying to, by using their fingers, apply a pressure using the fingers or the hand, and then based on that, trying to determine what's wrong with an organ below the surface. And so it's kind of like a remote sensing, okay? And this idea has been used a lot for the liver. So patients who have cirrhosis of the liver, the way they kind of diagnose that is they kind of, again, compress with the fingers or palpate. For cervical lumps, they do the same thing. Okay, so the whole idea is just to use your fingers and your arm, apply a pressure to some region, and based on that, you kind of try to make some diagnosis. Now, where palpation has been really, really successful is in breast cancer screening. So in 2011, this author reported that 57% of breast tumors are detected by the patient themselves, meaning a lady's taking a shower, she kind of feel around with her fingers doing self-examination on her breasts, and a lot of time these patients will detect a tumor or an abnormality themselves, again, using palpation. So we know that palpation is very, very successful, still being used, and have been used for a long time. So the question becomes, so if it's that great, why are we trying to make a new imaging modality, to do better than this? Well, the reason why we kind of spend a lot of effort, I think the field is about 20 years old, or a little bit over 20 years old, is that even though palpation is very successful, it has some really serious limitation. Now, one of the main limitations is if there's an abnormality, it can only detect this abnormality if it's very close to the surface. So for tumors that are very deep within the body, that you won't be able to sense those with your fingers. And the second thing is a lot of time when you detect these tumors or these abnormalities, they're very, very stiff, and it's very, very hard to detect tumors which have just a subtle difference in stiffness. So what we would like to be able to do is to detect very low differences between, let's say, the tumor and the surrounding tissue, as opposed to being a tumor that is much, much harder. And the reason why we want to do that is because by the time we detect this with palpation or by your hands, the tumor is typically usually in a very more advanced stage, all right? So we want to be able to detect it earlier. And the next thing is there are different types of tumors you may know. You have some tumors are malignant and some tumors are benign, and we cannot differentiate between a malignant tumor or a benign tumor purely by touch, okay? So those are the kind of the two main limitations that we want to fix. So if we go back to what palpation is doing and try to examine that, and I kind of highlighted some key words here, is that one, when you do palpation, you typically apply a pressure. And two, what you're really detecting is kind of size and consistency of some underlying abnormality, right? And now, if you kind of break that down a little bit, size is pretty obvious. When we think about consistency, then what we're really talking about is texture, right? So we can feel difference in texture, and that doctors use that as a way of differentiating between or diagnosing or detecting tumors. But another thing which we're doing here is that because we're applying a pressure, what this pressure will do, the underlying tissue will respond to this pressure. And what we can also do is that it will respond to this pressure depending on what the mechanical properties or the stiffness of this tissue is. All right. So if it's a very soft tissue and you compress, it will deform more. It will respond more quickly in response to that in response to that pressure. Or if it's a very stiff tissue, it won't respond as much. So the goal of elastography really is focus on the third thing. What we're going to try to do here is to visualize tissue stiffness or visualize the mechanical response of the tumor. And we're going to do that in response to some kind of force or some kind of mechanical stimulation to which we can apply to that tissue. All right. All right. Now, for those of you who are familiar with the literature, you will see that you can take all existing elastography techniques, so you can put them under 3 headings. You can say, we can classify them as being either quasistatic, harmonic, and transient. And this classification is really just based on the kind of mechanical stimulation that we're applying to this tissue. So for one, quasistatic is one where we just deform the tissue by a small amount. And typically, if you're using ultrasound, we probably deform this by no greater than like 2%. Typically, we do smaller. You can do a harmonic source where you just apply a mechanical stimulation, usually a vibrator, which is a source that is vibrating at a set frequency. And what that will do, that will send shear wave within the tissue. And then what you can do, once you send those shear wave in, you can use an imaging modality, usually ultrasound or MR or optics, and you can then measure those shear waves. And then the third method is one where you don't really use an external source per se, but you can use ultrasound itself to induce an acoustic radiation force. So this is kind of a transient response. And then you look and as you basically hit the tissue with that acoustic radiation force, it will send shear waves out. And based on those shear waves, we can use that information to derive the mechanical properties. All right. So we've worked with all three. A lot of the discussion that I'm going to have today is going to be focused around the quasistatic, since computationally that's the more interesting one. But we will talk a little bit about the harmonic and the transient method as well. All right. So if we think about quasistatic, all right. So this is probably the first systems that were developed. One was developed by John O'Fair, who kind of developed the field. And then another one was developed by myself when I was a student way long, centuries ago. And the ideas was this. So if you look on the system on the left, what they had here is an old mammography paddle. What they would do, they would put the lady's breast between this paddle, and then there would be a little window over which you have an ultrasound transducer, and that would scan backward and forward and acquire images, right? And these are one of the first clinical images that they got here, and that was reported by Brian Gara in 1997. And I think that this article, for those of you who are interested in it, it's in Ultrasound in Medicine and Biology. And what it kind of highlights here, it kind of highlights some of the strengths of elastography. So if you look at the ultrasound image here, what you see, this is an infiltrating breast cancer. And there's not anything obvious in the ultrasound image that there is a tumor there. My radiologist friends who look at hundreds and thousands of these images. Well, they can kind of see some information here because there's a shadow behind it. So that's kind of telltale sign that there's something there. But when you look on these images, you can't really tell per se. But if you say acquire an image, then you apply a slight deformation, you acquire another image, and then you kind of do some kind of localized template matching. You can create a displacement image. And then once you create that displacement image, then you can differentiate that and you can create a strain image. And so when you create that strain image, you can clearly see that abnormality here. And this dark region means it's much, much more stiffer, meaning it's not responding to that deformation in response to the surrounding tissue. Surrounding tissue is moving much more compared to this inclusion. Now, what this also highlights is that elastography in general will have much, much more high contrast than classic imaging modalities. The other thing it also highlights is that a lot of the imaging parameters that conventional imaging modalities are based on, whether it's T1, T2 relaxation time, speed of sound, backscatter signal strength, are not linked to mechanical properties, right? So a lot of time what you might find, there is an abnormality within the image, but it's not visible because the difference is what you're seeing in terms of the abnormality is based on mechanical properties rather than the intrinsic properties that the imaging system is designed to detect. And that's one of the reasons why we developed elastography. Now, the problem with this setup is, I remember when I was a student, our clinical collaborator described this as the contraption. They said they would never use this in the clinic because, first of all, it's too restrictive. In a lot of cases, what they've observed is that a lot of tumors is very, very close to the breast wall, to the chest wall, and therefore a device like this would never work. And so what we try to do instead is to go from this to this. So rather than having a nice computer control deformation, everything is nice and clean, we go one where we have the operators just deforming it, the transducer with their hands, and then had a lot of signal processing to deal with, outer plane motion and all of that, and then use that to create our elastogram. And here's one of the images that we created. This was, I think the entire region here is cancer. And this is phylloideous tumors of the breast. And the interesting thing about these tumors, they have these little globules, you can see these little bubble, little circular region here, and you can clearly see those regions in the strain elastogram. So we were pretty excited by that, all right? All right, here's another, the example that I just showed a while ago, that's all quasi-static. Now, if we look on the harmonic elastography, this is what it would look like. So as I said before, what we're going to do here, we're going to just basically put a low frequency vibrator. You can use a speaker, and you just introduce shear wave. And in this case, what Professor Parker is looking at the shear wave speed as it moves across, and he's using classic Doppler signal processing to just measure that shear wave propagation across this tissue. And then once you have that, so once you know the shear wave, once you know the shear wave propagation, you can work out the shear velocity, and there's a nice relationship between shear velocity on shear modulus and density. And based on that, you can calculate the shear modulus locally and create images like that. Now, the main drawback of this technique is for it to work, you have to have nice plane wave propagating. If you don't have nice plane wave propagating, this won't break. This will break down. It's pretty hard to calculate the shear wave speed and in turn calculate the shear velocity. All right, the other technique is the transient. So this is probably, I would say, the most popular approaches to elastography. Now, elastography tend to go through I guess it's like fashion. First, it was all quasi-static, then it moved to harmonic, and then it moved to transient, and I expect it will go around the circle again, just like fashion, right? So the idea here is this. So we take the ultrasound transducer, we program the system to really produce a really strong acoustic push. And so we call that, or a push beam. So it push, and once it pushed, then we measure the corresponding shear wave or displacement of the underlying tissue with this imaging pulses after. And what you see here is, this is kind of highlighting, showing a resolution phantom. So we have a wedge, and again, based on the shear wave speed, we can calculate the velocity using information of the density of the underlying tissue, and this is a corresponding shear wave speed maps that you would get, okay? All right, now I'm gonna go backward. As I said in my introduction, I'm gonna spend a lot of time on the quasi-static approach, because I think, like, for this audience, a lot of the reconstruction method, we have more experience using both quasi-static and harmonic for that. So we're going to spend a little bit of time on that. All right, I kind of illustrated this before. So what I'm going to talk about here is, here's a phantom. So this is just a piece of gel, and it's a gel within the gel, and one gel is stiffer than the other gel. And this phantom has 3 inclusions. And you cannot see this. And this was made by one of my students. 3 inclusion. There's one there, one there, one there. And it's not apparent that there's an inclusion there. And the reason why it's not apparent is because we designed it so it wouldn't be apparent. So there's no difference in the acoustic properties between the inclusion and the surrounding tissue, but there's a difference in the mechanical properties. So if you apply your strain imaging, then you would get an image like this. So this is again a response of this phantom to a 2% deformation force. You can clearly see the 3 inclusion. You know, this one is stiff. These 2 are stiffer than that one because it's much darker. But again, it's qualitative. It's not quantitative, because what we're really measuring is just a response. Strain won't tell you how, it won't give you a modulus, an exact number to tell you how stiff the tissue is. In most cases, under the special cases where the deformation is really, really, really small, on the order of less than 0.5%, there's a good relationship in terms of the ratios, but beyond that, there is not. The other thing that you can see here, if we look on the strain pattern in this image and this image, when they are this inclusion and that one, they kind of give you the impression, they kind of interact in such a way that they give you the impression that there's a 4th inclusion when there is not. So you can get artifacts due to that. Now, back in the days, and I think people still do this to some extent, what a lot of clinicians did was just to say, well, let's assume that the stresses within this field is uniform. And if the stresses are uniform, then I can just think of this as a stiffness map, as a Young's modulus map. So we're just going to say stress over strain is stiffness, and interpret these as stiffness map, which is incorrect. And when they did that, it really led to a lot of issues. So what I'm going to talk about is how we kind of solve that problem, right? So what we believe and what we know is that if you use that very simplistic approach to think about listography, you will get into trouble. And so the way to get out of those potential pitfalls is to really think about listography within the framework of solving an inverse problem. And just to illustrate how we're going to do that, this is how we're going to do it. As before, we can apply this to this framework. We can apply this framework to any elastographic imaging approaches. We can, and again, the only difference between these 3 approaches is dependent on the mechanical excitation. So it could be either quasi-static, where we're just applying a small deformation force. It could be harmonic, where we have an external vibrator, or we can use the ultrasound device itself to have a transient. Once we basically perturb that tissue mechanically, what we're going to do, we have to measure the response. And this is where your imaging come into play. So you can use ultrasound, you can use optics, you can use MRI, you can use CT. As long as a lot of imaging modalities are very sensitive to motion. Actually, a lot of time we actually don't want the motion because it typically screws up the images. But what we're going to use here is use the ability of those imaging systems to detect motions, and we'll use that to measure the response. Once you have the response, then what we're going to do next, we're going to couple that with some kind of model. And what that model will do, if you do it right, it will kind of link that response to, it will map that response to a mechanical parameter. And what we observe, both in different diseases and both in animals and patients, is that we expect to see contrast on the order of 2 orders of magnitude, if not higher, depending on what the state of the disease is. So this is a very high contrast imaging modality. All right. Now, I'm going to go back to this problem before. So if you remember this one, we had the 3 inclusion. You couldn't see it in the ultrasound image, right? And then we said if you did the strain elastogram, you could clearly see the 3 inclusion, and you also have some kind of artifact there. Well, we can solve the inverse problem. So if we solve the inverse problem, this is what it looked like with a very simple least square problem. You can see, we can see this is softer than these 2, and we can clearly see that we don't see an interaction there, but we do see some artifacts in these images. All right. We've also solved that for the harmonic case. I'm not going to spend a lot of time on it, but I'm just illustrating that. So this is a case where we use MRI to obtain time harmonic displacements. And this is a phantom. Again, it's got an inclusion there. And these are the displacement in X, Y, and Z. In the ultrasound images, we typically just show you the images, the displacement in one direction, because ultrasound is pretty lousy at measuring displacement and direction, which are not in the direction of in which the field is propagated. But MR doesn't have those issues, so MR is very good. And again, we use a similar algorithm to which we used in the previous one, and you can clearly see the inclusion lighting up there. Okay, so can do it with ultrasound, we can do it with MR. Now let's go under the hood and kind of explain what's going on and highlight some of the problems and strategies that we've developed to get around this problem. All right, as I mentioned before, in order to map the response to the mechanical parameter, we have to have some model, right? So for us, it's the classic Navier-Stokes equation. And this is what it looks like for for the harmonic case and the transient case. And for the quasistatic case, it's almost the same thing, except we just set that side of the equation to be 0. All right. So this is our model. And in this model, we have the shear modulus here. We have the Lamé constant. And these are our displacements. So this is a vector. So it's displacement in X, Y, and Z. As I said before, in ultrasound, we just use the displacement in Z and ignore the displacement in X and Y, and that has implications. And I will illustrate some of the implication of this, just solving this inverse problem just using one component. All right. Now, what a lot of folks have done is, if you understand if you know a lot about tissues, you know that they're made primarily of water. At least 90% of water, and so they're very incompressible. So if they're incompressible, then the divergence of displacement, you can almost set that to 0. And if you set that to 0, you end up with an Helmholtz equation, right? If you solve this equation in the frequency domain, this side of the equation just drops down to rho omega square, and there's a displacement term there, all right? And so you can really solve, your most simplest equation that you can solve is just this, that bit of the equation is gone. This is del square u, and you just divide that side of the equation where that is going to drop out to be omega square, and it's a simple inverse problem. Now, great algorithm, it's beautiful, it'll give you the best result if your data is perfect. So here's no noise, it looks perfect. And for this case, we just have this, it's a Gaussian inclusion. So it's not this sharp inclusion, it's just slowly, gradually fading into the body, into the background. And it did an excellent job recovering the parameter. We had 0.001%, just white noise to the displacements to this, and it falls apart, right? And so what we find with a lot of these direct inversion algorithms, they tend not to be as robust to noise. Different people have come up with different strategies for stabilizing them, but in general, they tend to be, they're faster computationally because it's just this is pretty straightforward to implement and solve, but the price that you pay, they're not as robust. Now, one thing I will say, as I go through this talk, you're going to see me, and this is, I tell my students not to do this, but I do it. So if any of my students who are listening, bear with me. We typically jump between the Young's modulus and the shear modulus, and they're related, right? And this is how they're related. So Young's, initially when I started this work, we did a lot of stuff using Young's, and then we convert these images back to shear just by using this equation where the V term here is really your Poisson ratio. And if you want to look on Lamé's, the Lamé constant, it's related to both the Young's modulus and the Poisson ratio by this equation. Actually, what we do now, we actually don't solve for E anymore. We just set up a solver to solve for both mu and lambda, because it's just a much more cleaner implementation. All right. All right. So let me tell you a couple of stuff that we observe. So before, the discussion so far has been, I said you have to apply a force to the boundary, and it's not 100% true, right? So there are actually two types of boundary conditions. So we can either apply a known force on the boundary, or we can just deform the tissue that we're investigating by a set amount, right? And so the case where we know the force on the boundary, we typically refer to that as Newman boundary conditions. And the case where we only know the displacement, how much it's moved by, we call those Dirichlet boundary condition. Now, if you solve the inverse problem, depending on the boundary conditions that you get, it might be truly qualitative or not, all right? And what do I mean by that? If we apply Dirichlet boundary conditions, so here's a case where we're saying we apply a known strain or a known displacement to the boundary, and that's our perturbation, and we're gonna set up the equation, we're gonna solve the problem. What you will find is that it will do a good job in terms of recovering the mechanical, in terms of recovering the ratio between, let's say, an inclusion and its background. If it's an homogeneous tissue, you basically won't be able to solve that because we don't have enough information. Now, if you did the same thing and now same problem, but this time you said, okay, I'm going to take information about the forces on the boundary and include that into my inverse problem. When I'm solving that, you can recover the exact properties of both the inclusion and the background. You can even solve the case where there's no inclusion. Now, as you look on this curve, you probably say, well, the dotted line is the true parameter. So this is a simulation. Dotted line are a true parameter. So why are we below that line? Well, the reason why we're below that line is, as I said to you before, this is an ultrasound case, is where we kind of model a three-dimensional object. So it's got displacement in both X, Y, and Z. But when we do the reconstruction, we only reconstruct using one component. And so when you do that, you actually lose your accuracy. So it tend to be not as accurate as it should be. And we estimate both in simulation and an experiment that typically it's on the order of about 10 to 15% error because of that, the fact that we only reconstruct using one component. Now, towards the end, I will describe some strategies that we've developed to kind of fix that problem and kind of show you how it improves things better. All right. Now, as I said to you before, the direct inversion approach, very fast, clean, especially when there is no noise in the data, but tend to be not as stable. So the approach that we typically use, at least in my group, is we tend to use an iterative approach. So we just use a standard least square method. And this is the first approach that we've implemented. Ignore the W for now. What we've done is just basically minimize the difference between what we measure to what we estimate using our model. And for a model, we just model this using finite elements. And then once we do that, we just minimize this with respect to E, the Young's modulus, and end up with this equation. Again, ignore the W. I'll talk about the W in a minute. And so we have our little Jacobian here. And so Jacobian transpose, and we multiply by the Jacobian, and that will give you our SCN. And because the SCN is almost zeros, it's pretty poorly conditioned. What we will do, we'll throw something on the diagonal to stabilize it, so to make it so that we can invert it. All right, so this is kind of for a regularizer. And then we do one more thing. A lot of time what we observe is as this thing goes around and, iteratively, the noise tend to accumulate. And so we have implemented a spatial filter, and all it's doing is if you're at a given node within your finite element mesh, it looks for its neighbors, and based on its neighbors, it do a weighted average, and that tend to suppress the noise as the algorithm iterates. All right, I've been saying to you to ignore the W. So our first implementation was this, but what we observe in practice, especially when we move to clinical cases, was that a lot of the time clinical cases or data is not as nice as simulation and definitely not as nice as phantom experimental data. So what we decided to do is to do a weighted least square where we'll use information about noise in the data or uncertainty in the measurements. And we had a way of predicting what the uncertainty in the measurements were. And then we'll use that to just kind of penalize areas which are, which we're not sure of compared to region which are very good. And in order to calculate that uncertainty, we kind of solved the Cramér-Rao lower bound. And this is some work a former student of mine did in 2007. Someone asked a question. Is it possible to compare signals from the left and right breast? Yes, you can. And we actually have done that in terms of, especially if, let's say you wanted to know if a person had a tumor and you want to see what is that stiffness relative to the contralateral breast. So we have done that. All right, coming back to this. So what this model does, so we didn't develop it, we just extended it. All right, so what folks have done, they model the Cramér-Rao lower bound, and there's actually one called the Ziv-Zaki lower bound. And if you look in the strain domain, this is what it looks like. It looks like, as you increase the strain, the quality of the data go up, 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 and then it just tanks, right? And from this, you can work out what's the minimum strain it can do, what's the maximum strain, and what's the dynamic range of the strain in terms of signal to noise. What's the maximum dynamic range of the strain? And you can use that to work out how good the data has to be in order for you to reconstruct. Now, what Prashant did, we kind of took this one step further. We said, well, my lab does a lot of work in beamforming, and actually Prashant's thesis was all about beamforming. And what we wanted to know at the time is how the different beamforming strategies, so whether we're using a conventional linear wave, whether we're using plane wave or compounding, how that affect the strain filter. And you can see, as if you look on compounding plane wave, it's much, much higher than the conventional. And if you come here, this is showing you the uncertainty. You can see it's the least uncertain. So we'll use this information on a pixel by pixel basis, and that's what we'd use to kind of weight our least squares. All right. Whoops. All right. Now, here's a nice problem. So this is, you know, it's always interesting when you show these results. You can show the case where everything is great, but I'd like to show the case when things go wrong, because they do go wrong, and they do go wrong a lot. All right, so when stuff is 0.5%, this is what the strain elastogram looks like. You can clearly see the inclusion. You can see some stuff at the bottom here. This is a reflection from the bench. But if you go to 5% strain, it just looks really horrible. And the reason why it looks so horrible is we just cannot measure, at least in one step between two images, a 5% difference, and it dies, right? Now, when you're doing freehand elastography, you know, if you're not careful, a lot of your data will be like this. And so in order to make your technique robust in terms of reconstructing, we have to kind of develop ways to deal with that. At the bottom here, I'm just kind of showing you, this is the standard least square for this case. Something wasn't right at the side here, so it just blows up. With a weighted case, you can kind of see an inclusion there, but you still see something there. This is what the weighting matrix looks like. This is for the 0.5%. The closer it is to 1, the better it is. And the closer it's to 0, you know, you're into trouble. That's what it looks like. And okay, whoops, I missed the image. Yes, all right. So here's the case where, so this is our low noise, standard least square, we nail it, right? This is our weighted least square, it looks much more cleaner. And I'm gonna talk about another case where we actually have a prior, and you will see that once we have the prior, it's even better. If we go to 5%, you can't really recover anything using the standard least square. If we go to the weighted least square, you get a little bit here, but most of the images you can't. And if you had a prior, a weighted least square plus a prior, you can see it stabilizes things a lot. So what is this prior? All right. So the way we introduce prior, we introduce it like this. So most of you would recognize, in this field, would recognize this is a T-Canus regularization. So we still do our weighting least square on the left, but we have this a priori information here. So E naught is our prior, right? And the amount, what this rho parameter is doing, it will allow us to say, how much do we want the algorithm to be more on, you know, the fidelity to the data versus the a prior. So if this is small, if this is 0, then it's going to be back to our standard least square. If this is very, very high, it's going to ignore that and then focus on that. All right. And when you minimize this with respect to E, this is what you get. All right. So we have E naught. This is a Jacobian and everything as before. And so the question you might be asking me, okay, you have E naught. How do you get E naught? Oops, going in the wrong direction. All right, so we get E naught. I'm going to talk about three ways in which we can get E naught. So one way we get E naught is we look at the strain elastograms. So the strain elastogram, if you just look at that, it will show you where the abnormality is. So what if we found the center of that and fit, in this case, we just fit a Gaussian, we assume it's a Gaussian inclusion, not necessarily true. We fit something there. And then what we will do, we will say, okay, what is the ratio between the strain in here versus the strain outside there? And then we'll use that to scale our Gaussian. All right, so this is our prior. And that's the prior which we use to solve that case. All right. I'll come back to this slide in a minute. Prior came up, was a big, for breast cancer, prior was okay, but where it became almost essential for us is when we were doing cardiovascular imaging. So for cardiovascular imaging work, what we wanted to do, we had this grant, and the grant was to develop method to detect vulnerable plaques. So vulnerable plaques are the type of plaques that either give you a heart attack or give you a stroke. So these are plaques where they just rupture, and when they rupture, they create a blockage, and that's what, either give you a heart attack or give you a stroke. And so the way we would do this is we'd have a very, very small intravascular ultrasound device. Will go up in the leg, into the femoral artery, right up into the coronary artery, and then would create images like this. So this is an intravascular ultrasound. We also know what the pressure is, so that was great. We know we can quantify it because we know the pressure within this thing. And as before, we'll just use our cross correlation analysis, and we can create displacement images. And then again, we feed that into a finite element and solve our inverse problem. Actually, when we tried this, it didn't work. The images that we got were very, very lousy. And so we really dived more into this prior. And so we came up with two prior. And Mike Richard, when he was a postdoc in my lab, did a lot of work on this. And what we decided to do, we had one thing which we call a hard prior. And for those of you who are familiar with mechanics, this is we kind of treated the problem like a lump parameter model. So what we did, we segmented different region, and then we just say, we're just gonna assign a single value to those regions. So if you have two regions, there's only two unknowns you're solving for, compared to thousands of unknowns in the previous model. All right. Now, I have this thing about having consistency between algorithms. So I wanted to take our standard least square method and should be able to just reduce it in a nice, elegant way. So what we did, we came up with this kind of mapping matrix. And what it is just saying, let's say we have two region or n region, what pixels are belonging to what, and then we multiply that by our standard Hessian, and then that will give us a reduced Hessian, and then we'll do everything as before. Right, so that was our soft prior. And then once you solve for the soft prior, we apply the same thing, the transpose of that, multiply by what we get, and it will assign those values back to all the values in our finite element. So it was great. Soft prior is great. Sorry, hard priors are great, except it's highly sensitive to how well we can segment the regions. If there are errors in the regions that we segment, it will produce problems. So we came up with a soft prior approach, which is really a different kind of regularizer we created. So we have this regularizer where, depending on the region, we'll have some U naught, and in this case, we use a log, and that allow us to penalize or kind of constraint based on region, but not as stringent as when we did it with a hard prior. So just to illustrate, here's some results. So this is a simulation. We had like 5 regions. So we have that one, D3 region, and that. And this is our hard prior. So we just segmented into 5 regions. And of course, the black is what it should be. And then, the one below, it's a hard prior. And again, it's a little bit lower because we are reconstructing from using one component. Now, if we use the soft prior, we relax, it's still constrained, but not as severe as this. So we can tolerate errors in the segmentation. You can see we just did a good job as well. You can see it have a little bit of more noise in the background, but it's very, very stable. Now, one thing I should add to this, in our hard prior, you actually don't need even to introduce regularization because you just have 2 parameters, or in this case, 5 parameters. So it's very, very, very robust to noise, but highly susceptible to errors in the boundary. And how it highly depends on how well you can segment these images. All right, so typically what we do in my lab, we usually start out with a simulation, then we go to some phantom. So here's a phantom. So we have a tube, but we made this tube. So it's a tube it's a layered tube. So there's 2 regions within this tube. This region is softer compared to that region, right? And so what we're gonna do is put water through this tube, right? So we have, and by changing the pressure, we can basically make the tube expand more or less, and we actually know how much pressure we're applying. And then we also push a intravascular ultrasound within this vessel. And you can see here, this is the intravascular ultrasound probe. It's really just a single element, a really tiny element that is just spinning around. And you can see I'm comparing it to the size of a pen, so it's really, really small. Actually, a lot of time when we're imaging patients with this device, the patient's awake, so it's minimally invasive. All right, so here are the cases that we have. So we segment this into 2 regions. So that's one region and that's another region. That little white stuff you see, that's the ultrasound. This is kind of what we call the ringing of the ultrasound transducer that you have there. This is the displacement images or radial displacement images we created by, again, just doing kind of template matching and several template matching or cross-correlation analysis, as we call it. And then this is when you differentiate this, this is the resultant strain image you get. And now you can see the strain images here, right? So we could have selected a prior from this, or we could have selected a prior from that. We chose this because when we actually created this phantom, there was a difference in acoustic properties between the 2 regions, right? When we do our standard least squares, this is what it looked like. Couldn't identify the region. This is our soft prior reconstruction method. You can see some, I know it's soft prior because you can see some variation within the 3 region. And this is our hard prior reconstruction. So very much similar. And again, what we did, we took samples from this region and that region. We did some mechanical testing. And when we did that, we found out that, at least for this case, we're on the order of 15 to 20% errors. And again, most of that error is due to the fact that we're only using one component of displacement. All right, we have also done studies in animals, and that's the next step that we typically do. We created an animal model in New Zealand white rabbits, and we give them plaques. So for those of you who are interested, it's a plaque injury model. We go in there, we damage the rabbit, and then give it a very high cholesterol diet for a couple of months, and then develop plaque. We measure the pressure with the vessel. We'll take, in this case, we'll measure the pressure at 2 different points. And then again, we'll take images at these 2 pressure points, measure the displacement, in this case it's strain. Again, combine the mechanical model, segment the image to highlight the different regions, and this is what you get. So these are the ultrasound images that we use to create this one, and this is the modulus images that we create using our soft prior reconstruction method. All right, for the rabbit, we found this case where we identified a region on the ultrasound which didn't look which we thought was different. And so we divided into 3 regions. And when we divided into the 3 regions, we found that that region was softer than everyone else. And then when we look on the histology, we found out that there was indeed some abnormality here, which was it was kind of a thrombosis. When the vessel ruptured, it created that thing there, which we detected there. All right, so we're pretty excited by that. We've also tried it on patients. So we had some work with Boston Scientific. And so they make ultrasound, intravascular ultrasound systems. In this case, we segmented into 3 regions. And based on that, we could say that region is softer than the remaining region. So it might be a lipid or fatty plaque, but beyond that, we can't really say anything more than that, right? Unlike the rabbit, which we can kill and do histology, we can't do the same thing with the patients. So we saw some differences, but between regions, but we can't say for sure if the values that we estimated there is truly what there should be there. So we're doing more animal studies to kind of confirm that. All right. The other way that we have obtained information is to combine different imaging modalities. So not a PhD student of mine, Himanshu Shekhar, who's now a professor, what we did when he was doing his thesis, we were working on contrast agents. So we're looking at nonlinear ultrasound imaging. And it's actually the work that we were doing here was also to detect vulnerable plaque, but from a different perspective. We weren't looking at elastic properties. What we were looking here is to see if we can see these tiny micro vessels. So it's a vessel within a vessel. And according to the literature, the more of these vessels that you see, it's telling you that this plaque is kind of the type of plaque that is likely to rupture. Right. So what Himanshu did, he developed a system, he worked out the regime, the pulsing, and he developed a system where he can visualize these vessels within vessels. And so here's an experiment which he did. He created this vessel, just like the one we did before for the elastography, but he had these really, really tiny little vessels in it, and he's flowing contrast agents with that. And then when he flows contrast agent, what he will have, you can see when you look on your fundamental images, so these are the standard images you get from an ultrasound, you can't really see these vessels, right? But he was looking at subharmonic. So what he's doing, when these bubbles oscillate at very high acoustic pressures, what they do, they behave non-linearly. So let's say what it does and what that means, it acts like a nonlinear device. What that means is if, let's say you have a 18 megahertz signal, you may see another signal at 36, or you may see another signal at half that. So we call half that as sub. You can have first harmonic, second harmonic, third harmonic. As you go to the high harmonic, the amplitude go down, but the subharmonic is very, very good because a lot of time tissues by themselves doesn't generate subharmonic signals. So here you can clearly see these 3 vessels. So what we decided to do, well, I didn't do it, 2 students who were working. So Steve Hunsiger was doing a lot of the coronary, the vessel work, and Himanshu was doing that. They got together, and what Steve did was to use the harmonic imaging to work out what where these microvessels are, right? And then what he did is to say, what he wanted to find out was what was the maximum stress in these vessels. So the question he had was, okay, if I know the mechanical parameter, if I solve the inverse problem, work out what the Young's modulus distribution or the shear modulus distribution is, I know the pressure within the vessel, I can use those 2 pieces of information to work out what the stress is. The stress within that vessels are, because like that is what will dictate whether the vessel will rupture or not, all right? And what he observed is that if you look on the maximum principal stress, and if you just do your classic solve the inverse problem without using that a priori information about where that vessel is, the maximum principal stress that you will see will be much lesser than what it should be if you don't use that a priori information. So this was pretty good, and we were very excited by this result. All right, the last method that we've used to gain a priori, so this is some work we're doing with Nargis and machine learning. Everyone's doing machine learning nowadays, and they're the machine learning gurus, at least where we are. And so what they've done, they kind of developed the neural network, and what this neural network will do, you'll solve the inverse problem, and then it kind of does this denoising situation. And when you do this denoising, it will give you, it'll take the image that you reconstructed, it'll go through this convolution layers, and then it will give you a cleaner version, and that cleaner version is kind of our prior. I'm not going to go through this, but I'll show you this. So this is your input image, right? It's kind of cruddy. If you put it through this thing, it kind of reduces a lot of the noise, right? It's still some noise there, and I think if you push it even further, you'll get it even more. And if you take the difference between this one and this one, you can get, this would be the difference between these two. This is what it should look like, and this is what it is like. And they're doing this, the companies to total variation. I believe actually this is the future for as I
Hey, Marvin, I think we lost your slides. And you're muted, so you may need to unmute yourself back.
Okay, here we go. Let me go back. Something
I
went
think
wrong.
there was maybe a connection issue, so your voice started becoming a little choppier, and then we lost the slides. But now we can see and hear.
Okay, all right. So I'll continue from here. So did you get me here?
Yep.
Okay, perfect. All right. I actually think this is the way to go. A lot of the time, when we select our prior using the imaging, go and segmenting, sometimes there's features that we cannot see. So I actually believe that if a machine learning algorithm can actually pull out those prior information, give us information that we can't see, that will definitely strengthen the technique. All right. Now, the other thing that we're doing is we've been collaborating with Tom Howard, and Mike is graduate student, and we're trying to fuse this method with robotics. And the idea here is we're actually trying to see problems. So the first problem is the easy one, which I'm going to talk about today, is one where we said, well, if you're doing something like in breast imaging, we don't know what the pressures are or the forces are on the boundary. If you have a robot, then we can work out what the forces are because it's got these 4 sensors there, right? So that's the first one, right? So I'll describe that. And then the other case that we're looking at is to say, well, and Mike is still working on that problem. We're saying, Mike, what if you use the elasticity information, you use the force sensor, and so imagine that we're going to replace the nurse with the robot. We're not going to do that, but let's imagine. We don't want the robot to crush the patient. So it's going to use that elasticity information and going to use that in a control way to control how much deformation it's going to apply. I won't describe that one because we're still working on that, but the one that we're going to describe here is the one where we inverse problem, and the reason why we wanted to do that, that will make it truly quantitative. All right. Can you still hear me?
Yes, we lost you for a couple seconds, but I think it's fine.
I can tell when you lose me because my thing flashes back to me that unstable.
Mm-hmm.
Okay, all right. So here's how we kind of calculate the force. So the force that the robot is applying is going to be a function of how deep we want to penetrate Young's modulus, the Poisson ratios, the ratio of the radius of this thing here. So in here is our ultrasound probe, and it's just this is the radius of this little disc. All right. And so if we have that, then we can calculate the forces on the boundary. So it's kind of it's a multi, we're going to use the inversion to give us that. We're going to know, well, the radius is pretty easy. The penetration depth is easy, but we're going to combine all this information together and do that. All right. So in terms of working out what the forces the thing is applying, I think this robot, the Sawyer robot, it's got 7 joints. And so by knowing the angle of the joints, you can work out this, a nice little, you can use these joint information to work how much spectrum will move, all right? Here's a little test demonstrating what we're gonna do here. So we have a gel with an inclusion. It's gonna come down, it's gonna deform it. We're gonna collect it. This is our ultrasound device there. This device here is controlled by the robot. And then what we'll do, we'll take samples from, this one is just a simple inclusion phantom. We'll take a sample from the inclusion versus the background, and we'll do mechanical testing, and we will compare what we get by solving the inverse problem with this versus solving versus what we measure independently. Now, we're going to do a few little things different to what we've done before. So before, what we've done, we solved the inverse problem like this. Now we're going to introduce, and so you can think of this as being more deterministic. We're going to introduce some variability in our model. And so we're going to have right here, very, very similar. We're going to have our covariance matrix. I'm going to introduce that there, and that we believe will make the thing more robust. And in terms of variability, it's going to take the covariance matrix is going to take into account variability in our displacement, variability in our ability to measure forces. And so it's both our ability to measure the mechanical properties and also our ability to measure the forces using the robot. All right. So here is what we have here. As before, if we did everything nice and we look on the displacement, this is what the axial displacement would look like. And this is, if we model, this is what it would look like. And you see there's good agreement. This is a cross correlation coefficient at every pixel. And it's very, very high, which tells us that we have a lot of confidence that this is good. Here, I'm going to show you, so what Mike has done here, we've did 201 compression. So we're compressing small amounts and doing 201 compression. And what we are calculating here is the properties between consecutive pairs of compression. And you can clearly see here, you can clearly see the inclusion. Nice, it lights up. And here, this is what we call our uncertainty map. So if you want to think of, all right, if you think of standard least squares and you calculate the covariance, that would be like all the terms on the diagonal. And we just display that in the image. And this is what it looks like. It's telling you that the inclusion is highly, we have a lot of confidence and so forth. If we compare what we measured to what we have, you can see there's good accuracy between these two. And the reason why the error is much, much lower than what we had before, with the robot, we can do very, very small compressions. So you can kind of, the smaller the compression, you kind of get away in terms of really, really needing two components. If you go for a bigger compression, so when Mike was doing this, I think the compression was on the order of 0.1% between those little, between any two images. As you increase the compression, then you really need both components to do a good job. But it kind of shows you here using the strain information, there was no prior in this case, the strain information, we did weight it based on using information regarding uncertainty. We can recover from this. And it seems that including forces within this problem also make the problem more stable as just in terms of not including forces. All right. Last thing, I'm almost done. I'm going to talk about non-invasive vascular elastography. So this is the case. It's similar to our intravascular work, but it's always interesting when you write grant proposals, right? You write a proposal, and we did get the grant, but a reviewer through comment was, well, intravascular is still minimally invasive, and you could, by introducing a device in the artery, actually cause an heart attack. So why don't you come up with something non-invasive? So I did. So we came up with this thing. So the idea here is if you just look on the carotid artery. So this is the artery in your neck. So here you can see on the right, I'm scanning my neck. If you just look on the carotid artery, there's a lot of data there's a lot of stuff in the literature that says it's kind of like pipes, right? So if you have a bad pipe, let's say you look in your house and you look in the pipe in your kitchen and you find that it's really corroded, the chances are that all the other pipes are just as bad is very, very high. So there's this clinician who made that hypothesis that if you look in the carotid artery, if that is in bad shape, it is highly likely that further down the vascular tree is also in bad shape. So maybe before you go to this intravascular technique is try to just take a look in the vessel in the carotid artery, and you don't need, it's invasive, and get a sense of what's happening. All right, so again, same problem. This time, it's a vessel as before. We're gonna take, but we're looking from outside in rather than from inside out. Same vessel, 2D cross correlation. This is what the axial displacement would look like, and this is what the lateral displacement will look like. So you can tell the lateral displacement is lousy, right? And if you calculate, and then what we would do, we'd take this, we'll calculate, we take our displacement, calculate the displacement using the gradient in both X and Y, and then that will give us our corresponding strain. Now, we looked at this problem and actually, let me go back to this one. We looked at this problem and we said, okay, let's forget about reconstruction for a moment, right? Let's say what we would like to do when we do our measurement, we're measuring in Cartesian, axial and lateral. And what we really would like, it's cylindrical, right? So we really would like to see what the radial and circumferential strain looks like, right? So this is when we do the coordinate transformation, this is what it looks like. But to do this coordinate transformation, you really need both components. Now, this is what we measure. We can measure the radial axial displacement very, very well. The lateral component, we do a lousy job doing that. And so when you do the coordinate transformation, this is what the radial strain would look like, and this is what the circumferential strain would look like. Total garbage. So we try to tackle this problem first. The goal of what we wanted to do, and we had 2 PhD students working on this, is to figure out how can we make this better? To improve our ability to measure lateral displacement, but maintain our ability to measure axial displacement just as well, right? So what we did,
Marvin?
yes.
Hi. I think in the interest of time, we should start wrapping up and.
Oh, sorry,
and
I lost
getting to
track of time. All right, I
There
will
are a few
wrap up.
questions as well, so we would like to have time to answer them, and then.
Sure. All right. So what I will say is this: we had a technique known as synthetic aperture imaging, and we have a technique known as plane wave imaging, and that allows us to solve that. The problem is really this. It's, if you think about ultrasound, what we have is our blurring function. You want to think of it as a multiplicative noise, and that's our PSF. And we want to reduce the lateral extents of our PSF. So we can do that. So when we do that, if we do synthetic aperture and we do plane wave, so we're images at multiple angles, this is what synthetic aperture is. This one is plane wave, and this is compounded plane wave. And so if you take either this one and this one, then that will solve it. All right. What I will show you here, last image. All right. So we took that information and we try to ask ourselves a question. If you look on cardiovascular disease, there are two types of cardiovascular disease. We wanted to know, actually, if we look at cardiovascular disease, we want to know how well we could use our mechanical properties to predict or to detect this cardiovascular disease. We create this model, it's a ligation model. We reduce the flow in one vessel, we keep the flow in another vessel going. And then what they typically use in the clinic is to look at the intermediate thickness. So when you do that, what you'll find out that if you look 1 week after we created this model and you look on the intermediate thickness, you don't really see a difference. Control versus the ligated. But if you do the elastogram, you clearly see a different, 1 week earlier, you see a huge difference between the ligated model or the disease model. And even 2 weeks later, you see a greater model. So what we were saying here is that just using the mechanics, we are much more sensitive than that. All right, I'm gonna wrap up now and say the last thing that we have done, we've also done some work looking on pancreatic cancer. And what we wanted to know here is how well we can use, how does stiffness impact the ability to deliver chemotherapy to pancreatic cancer. And so what we did this in collaboration with Brian Pogue at Dartmouth. They use an optical method to measure how well a drug is being delivered to a tumor. And then we use elastography to work out how the stiffness of that tumor impact that. And what you can see here is there's clearly an inverse relationship between the stiffness, so the stiffer the tumor is, will impact how much the drug will be delivered. All right. Thank you, and sorry I went on so long, but thank you very much.
Thanks, Marvin, for the comprehensive talk, and we have a few questions.
Sure.
And I think in the interest of time, we will go straight to the audience questions. The first question is from Joseph Richardson, and I'll enable Joseph to speak as well. The question is, thank you for the great overview. When applying boundary conditions to your models, are you only assuming the conditions only for the transducer tissue interface, or for all surfaces? Do you model the other surfaces as an infinite media with PMLs? If so, how are these treated in the solvers?
Okay, so that's a good question. So for the breast, model just the base of the breast, and we also model the top where we're applying, and we ignore the sides, right? And the way we get those, so if we think about the case where we have Dirichlet boundary condition, we're saying those measurement points where we measure those displacement, that is what we're going to use for that. For the intravascular work, what we've done, we've kind of created this model where we said the vessel, what would be the boundary condition at infinity B, right? So on infinity, it will be 0, right? So we created this huge model and then make a subset and then do a reconstruction from a smaller plane. And that's how we apply the boundary condition. Did that answer your question?
I think Joseph unmuted the mic, but maybe we can't still hear.
Okay, all right.
But otherwise, we can go to the next question from an anonymous attendee. Does elastography always, is it always effective in detecting cancerous tissues at early stages?
That's a good question. That's still under investigation. So it's, I would say it's a hard question to answer, and I tell you why. It's hard to answer, you know, in a lot of these cases, unless you're doing surveillance, you're actually looking for these tumors, then at least if in patients, then that's the only way I can say how well it can detect it or not. In animal models that we have done, we've shown that it works well in detecting very early in, you know, if we create an animal and we look in on the progression of the tumor over time, then yes. But in patients, it's until elastography become part of routine breast scanning, breast surveillance for women, then it's going to be hard to answer that. But my working hypothesis is that yes, it should.
Okay. Next question is from Syed Saneh, I think. In the KB product, K is M by N, and that is
Yep.
not square. And you said B is a Hessian matrix. Is that right? That's the question.
Yes. Yes. So the S. All right. So the easiest way to think about this is we have the Hessian matrix, and what we're going to do with our Hessian is we're going to divide. We're going to look on. We're going to segment our images, and we're going to group region in your Hessians which are similar, belonging to one region, and we're going to group the other regions. We're going to collapse your Hessian depending, or the sum is really just a summation, right? Depending on the different region that you're doing it. So yes, B is, if I remember the equation, B is definitely our Hessian, original Hessian, and K will be the different region that we're segmented in.
Okay. Maybe let's go to the next question by Kirti Anand. Why is there streaking in the cross correlation output on the previous slide? That's a question.
What? Say that again?
Why is there streaking in the cross correlation output on the previous slide? I don't know which slide they're at.
Oh, I know the one. So you're talking about the one with the robotics. All right. Yeah. So he's talking about the striping artifact. So the stripe artifacts in the cross correlation is also in the strain image. It depends on the different parameters that you use for your window size and all of that. We didn't try to optimize it for that one. We just took an image. The student just, I said, give me a correlation image, and that's what he did. But there's a lot of work showing that if you look on the work of Tommy Verghese, they've investigated this phenomenon a lot. It depends on how much strain is applied, and it depends on the type of window, that is the length of the windows that you're using, that creates those artifacts. And it is in the strain image, you just can't see it as much.
Okay, and the last question is from Fernando. I think Fernando is in the audience, so I would allow Fernando to speak as well. The question is, isn't the 2D elastography problem with ultrasound inherently ill-posed? Shouldn't the inverse problem work with data from matrix ultrasound arrays in a 3D scanning sequence?
Yeah, not necessarily. So you're right that the 2D inverse problem is ill-posed, and that's the reason why we're pushing for more a priori. Actually, if you want to solve that problem, I think having volumetric data or even 3D, even if you have 3 components, still won't make it well-posed. The way you need to make it well-posed is to basically get independent estimates of your displacement. So what that means, so let's say you compress from the top, you compress from the sides, right? And then you're using 3 pieces of information, and for those 3 different compressions, you're having 3 components of displacement. You'll have a bigger Jacobian and a bigger SEM to solve, but that's how the problem would be more well posed. So the matrix will help with having the matrix array, assuming that you can measure displacement well in all 3 component will help with your accuracy, assuming that you make the problem more well posed, but having that data by itself won't necessarily make it well posed, if that makes sense. Does that make sense to you?
Yeah, so you basically have to poke it in the 3 dimensions and also receive data in those 3 dimensions almost
exactly.
To get like the tensor, the full tensor data. Yep, that makes sense.
That's it. Yep.
Thanks.
Yep.
Okay, so that completes the audience questions, and maybe I had just one question, which was when you're talking about the machine learning part.
I knew you were going to ask me that.
For denoising, I was wondering, was the data that you used for training the network sort of simulated, or was it?
This was simulated. So what we've done now with Mushtaq, we started with simulated data, and what we're doing with Nargis' student, we are now going in to do phantom studies.
Okay, that's great. I think that was one more question. So you were using repeatedly weighted least squares.
Yep.
Is there a preference to this or versus a different statistical model? Is that?
Oh, no, I actually think the statistical model is the way to go. At the time, this was like the easiest thing. I say, hey, we have this data. We were at the time we were doing some work trying to solve the chimera lower bound just for our displacement estimator, right? And so we thought that, well, if I know my uncertainty, well, let's do a weighted least square. But I actually think the way to go is to do it more statistical. Mm-hmm. And in our robotic work, that's what we're doing now.
Okay, great. So that's about it. I think I don't see any more questions from the audience. Yeah. So thanks again, Marvin, for joining us in the SPACE webinar series. And for the audience, for those of you who have stayed behind, we'll have the next SPACE webinar this time 3 weeks later. So it's going to be on June 23rd, and the information will be posted on our SPACE webinar website. And if you are on the mailing, if you have registered, you'll also get the reminders that would have the date information, but the talk information will be on our website, and we'll have that on soon. So that will be the last webinar in our season 2. So hope to see you next time.
Well, thank you for having me.
Thank you for your talk, Marvin.
Okay, bye.
Bye.